Hi everyone. When you drop some water on the floor and you wait for some time, you'll see the water is not there anymore. What happened to the water? It got evaporated. Now same thing doesn't happen when you drop some salt on the floor, right? It stays there. It doesn't get evaporated. Now why? Now the simple answer is water is liquid and the salt is solid. So in solid, the molecules are attracted more strongly. So it's difficult to break the bonds and therefore they don't evaporate that much easily. And that is the right answer, obviously. But how do we go into more detail? Okay. So now you have to understand that water is made up of molecules and each molecule has two hydrogen atom and one oxygen atom. Whereas in salt, for example, NaCl salt, it is made up of ions, Na plus NCl minus ions. Now the ionic bond is formed in such a way that if one atom you take for sodium and one atom of chlorine, then the sodium gives one electron completely to the chlorine, completely. So what happens? The charge on the sodium atom will be plus E and the charge on the chlorine atom will be minus E, right? So sodium atom will have a charge of plus E and chlorine will have a charge of minus E. And when they are at some distance r, the electrostatic force is given by the Coulomb's law, which is proportional to the product of the magnitude of the charges and the distance squared, isn't it? So you can see this product is E into E. Try to remember that. Now in case of water molecules, the atom does not give completely its electron to the other atom. Instead, the valence electrons are shared in such a way that there is an uneven distribution, meaning the valence electrons revolve in such a way that they spend little bit more time towards oxygen than compared to hydrogen. In the language of quantum mechanics, you can say the probability of finding the electron is more near oxygen than compared to hydrogen. And that's why the oxygen atom becomes slightly more negative, whereas the hydrogen atom becomes slightly more positive. However, this time electron is not completely given, right? So the charge of the oxygen atom is not complete minus E. It doesn't receive one full electron. It is just a uneven distribution of the electrons, and because of that, the partial charge, if you calculate for oxygen, is minus 0.66 E, which is not 1 E like in the case of chlorine or in the case of sodium. And the two hydrogen atom, each one gets a partial charge of plus 0.33 E. Total should be 0 because overall it is neutral, right? The molecule as a whole is neutral. So this should be 0 total, this should be also 0. So now when you have two water molecules, the end which is slightly more negative and the end which is slightly more positive, they attract each other. In other words, the oxygen side will attract the hydrogen side of the other molecule. And here you can see the charges participating is not E like in this case. It is less than E, isn't it? Here the product of the charges will be 0.66 E into 0.33 E, which is approximately 0.7 into 0.3, which is 0.21 E square. Whereas here the product was E into E square, right? So this is 1 E square, this is much less than 1. So this is the reason why the ionic bond is much stronger than the force between the water molecules, right? However, in this video, my main aim was to show you that the force between the ions is actually a long range force, and the force between the water molecules, which is also called dipole-dipole force, is actually short range. So that is where I want to go. Now the force between ions is basically the Coulomb force, the electrostatic force of attraction, which is given by some constant product of the charges divided by square of the distance between them. So the Coulomb force, which is the force between the ions, is inversely proportional to square of the distance. However, the force between the water molecules, as we have seen, one end is plus, one end is minus. So where there is separation between minus and plus charges in a molecule, such a system is what we can call as electric dipole. Okay, and the dipole moment is taken from minus to plus. And each water molecule will have some dipole moment P, which is the product of the charge into distance between the charges. Now, when you have two water molecules, okay, the attraction between these water molecules, the attraction between this dipole and this dipole is actually short range. So why it is short range? Let us try to see. So let us first find the formula for force on a dipole. So imagine along x-axis, I keep a dipole minus q plus q. Let us assume the dipole is short. So this distance is quite small. I will represent it by dx. Now let's say we have a electric field capital E in this direction. Okay, electric field due to some source charge. Now if electric field everywhere is same, then the force on the dipole will be 0. Why? Because plus q will feel force in the same direction of electric field QE, and minus q will feel force in opposite direction of electric field. Magnitude will be QE. So total force will be QE minus QE, which will be obviously 0. However, if you have a non-uniform electric field, then the electric field here, if I say E1, here it will be E2. It can't be E, same everywhere. So the net force will be now not 0, it will be QE2 minus QE1. So if I take Q common, it will be E2 minus E1, which can be written as change in electric field. But this change is very small, so the electric field change also will be small. I can write it as dE, right? E2 minus E1. Then how do I bring dipole moment now? Well, I will multiply with distance between the charges in the dipole, and I will divide by the same distance. Now this Q into dx is called dipole moment P of the dipole, and here we have the rate of change of electric field with distance. So this is the formula for force on dipole. Okay, so if a dipole has dipole moment P, it will feel a force of P into dE by dx, and where E is the external electric field, which should be uniform or non-uniform? Non-uniform if you want dipole to feel a force. Now let us consider the force between two dipoles, which we can say dipole-dipole force. Now, as I told you, the force on this dipole due to this dipole will be dipole moment of this into dE by dx, right? And this E is created by, remember, this dipole, isn't it? Because this E should be external to this dipole. So this E is created by this dipole. Now what is the electric field here due to this dipole? This is axial line for this. So for axial line, what is the electric field? 2kp by distance q. Remember, this P is for this dipole. So if I write P1, P2, the one which is feeling the force, that dipole is this, and the one who is creating the electric field is this dipole. Okay, P1. So now to find the force, we just need to substitute this E here and take the differentiation, right? So P2 will come here, and differentiation of the electric field 2kp1 by x cube. Now constants you can take outside, 2kp1. So 2kp1 p2, differentiation of x power minus 3. Now remember, I want only the magnitude of the force. Direction of the force I will let you know how to find. So this will be 2kp1 p2. Now differentiation of x power minus 3 will be n. This is your n, x power n minus 1, so minus 4, which is minus 3 by x power 4. but I want only the modulus, so it will be 3 by x power 4, which is 6k P1 P2 by x power 4. So you can notice, students, that the force between the dipoles is inversely proportional to not distance square. It is inversely proportional to distance power 4. So for ions, the force was inversely proportional to distance square, and for dipole-dipole, the force is inversely proportional to distance power 4. And you know that r power 4 increases faster than r power 2, isn't it? So since r power 4 increases faster, 1 by r power 4 decreases faster. So this force decreases faster with distance. So if distance is doubled, then double square will be what? 4 in the denominator. So this force will become 1/4. Whereas this force will become double power 4, 1 by 16th of the original force. So dipole-dipole forces becomes very weak the moment the distance increases, right? So the moment the distance increases, the force becomes very weak, and therefore it becomes very easy to break those bonds. And thus we can understand why water evaporates even at room temperature, whereas the ions in the salt crystal does not, right? Now how to find the direction of force on this dipole due to this dipole? Now we know this dipole has dipole moment P1 this side, so it will create electric field in axial line in the same direction. So this will create electric field this way, remember, okay? Now this is positive charge, so force will be this side. This is force on positive charge. This is negative charge, so force will be this side. But remember, this is nearer to this the dipole. This end is nearer to the dipole. So this force on the negative charge will be greater. Therefore, the whole dipole will be attracted this side. Similarly, this dipole will be obviously attracted that side. You can check that yourself. Okay.